everybody. I'm going to the AP conference today, and so I thought I would record your lesson for you. That way you can get on with bond energies and we can move on to the next thing next week. So here we are. We're going to learn how to calculate delta H of reaction using bond energies. And so I just want to remind you, here's my bond. Oop, don't roll away. Okay, so here is a bond between two atoms. And if I want to split up this bond, if I want to break this bond, I have to put in some energy. And so that's going to require me to pull them apart and separate them into their individual atoms. And so, remember that breaking bonds requires energy. Woo! And as you just saw, forming bonds is a lot easier. It releases energy. And so with those two pieces of information and a whole table of values, we should be able to calculate the delta H of reaction. So we know that the delta H of reaction is going to be equal to, remember this guy? That's the sum of the number of moles, N, times the bond energies. Minus the sum, then there's the N again, number of moles, and the bond energies again. But remember, bond energies are always given as positive values. So we learned that in that activity that you did where you worked your way through an understanding of bond energies. And so bond energies are always, always, always positive. And that's not true of delta H values. Delta H values can be positive or negative, but bond energies can't. And so for that reason, when we start to think about what's going to be here and here in this equation, we have to be very careful. And so we know that this is going to be a backwards formula. So this is going to be the reactants. So the bond energies of the reactants, which are positive, take away the bond energies of the products, which are also positive, can give us that delta H value. And that delta H value can end up being a positive value or it can end up being a negative value, depending on whether it takes more energy to break bonds than it does to form them. And so we're going to look at what that means in just 1 second. We're going to find the delta H of combustion of propane. The formula for propane is C3H8, and we're going to do that using bond energies. Okay, so let's write an equation first. Some of you still are struggling with how to write a combustion reaction, and I will remind you that no matter what, if it's combustion, there has to be some oxygen involved. And so you're always going to need to include the plus O2. And that's going to give us CO2 and H2O for complete combustion. Incomplete combustion gives us different products. And hint, hint, when you're doing your lab later, you might think about whether or not when you burned your cheesies, that was incomplete combustion or complete combustion. All right, so I have 3 carbons here. I'm going to need 3 carbons there. I have 8 H's on this side. I'll put a 4 here. 3 times 2 is 6, plus 4 gives me 10, so I'm going to need a 5 right there. And there's my balanced equation. So in order to determine delta H of combustion using bond energies, I'm going to need some Lewis diagrams because I have to be able to count the bonds. So that's what I'm going to show you next. I love my really high-tech camera here. Someday I'll get a fancy tablet and you won't have to see my hand when I do this. All right, so here is propane. And if I was in the classroom with you right now, I would ask you how many carbon to hydrogen bonds there are. But since I'm not, and you guys don't answer me anyways, let me just count them up. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 C to H bonds. Then I'm going to count how many C to C bonds there are. So there's one here, and there are only 2 C to C bonds. So that's for my first reactant. My second reactant is O2. And sometimes when people draw O2, they forget that O2 doesn't have single bonds. So here's a Lewis diagram, and you can see there's a bond here, and there's a bond here. So O2 molecules are actually double bonded. Now, note this 5, okay? In one molecule of O2, there's one O to O double bond, but because of the 5 in front here, we really have 5 O to O double bonds, which I'm going to count up. So, I'm going to draw a line to divide my products from my reactants. So let's take a look at the products. Again, it helps to draw a Lewis diagram if you're not sure what these molecules look like. Oxygen has 6 valence electrons, carbon has 4. There's a bond here, and here, and here, and here. So what we really have is 2 C to O double bonds per one molecule of carbon dioxide. But there are 3 molecules of carbon dioxide in this balanced equation. So what I really have is 6 C to O double bonds. I hope everybody can see that. If you can't, sometimes it helps to draw out all 3 of these molecules, and then you can count them individually. Okay? All right, H2O. We've drawn H2O so many times that I don't think a Lewis diagram is required. There it is. I like to show my lone pairs because those are important for other things. So, in this one molecule of H2O, there's an O to H bond here, and there's another one right here. So really there's 2 O to H bonds for every single one of these water molecules. But we have 4 water molecules. So 4 times 2 gives me 8. So that is going to tell me the count of each bond type in this reaction. And then from here, I can take that information and I can use my table of values, which I'm going to grab. On page 688 in the book, you will see here are the values that I'm going to use. There is another table at the back of the textbook that you can use, and that will have more bonds for practice questions later. But for right now, this will help us with what we need. So, that's page 688. So remember, all these bond energies are positive. There are going to be no negative numbers whatsoever. Ooh, crookedy. Okay, so let's make a list of values. I know that for every C to H bond, the enthalpy value for that, or the bond energy value for that, is 413. So this one is 413 kilojoules per mole. And then for C to C bonds, that's 346. I'm not going to draw in all these units. It's going to make it too messy. And then for our O to O double bonds, that is 498 kilojoules per mole. Then I can look up the C to O double bonds And if I do that, I find out that the value is huge. It's 745 kilojoules per mole. And for O to H, it's going to be 467. So those are all the bond energy values that I need to be able to calculate the next part of this question. And so this is taking me forever to do, but the good news is that when you start doing them and you get the hang of it, it'll actually be pretty quick. Okay, so I have to start filling this into my equation. So my delta H reaction is going to be equal to the sum of, remember, so I'm going to add up some stuff here, and it's going to be N, and the N is the number of bonds. It's the number of moles of bonds. Okay, so this isn't the reaction as if 8 C to H bonds were breaking, but as if 8 moles of C to H bonds were breaking, because remember, this is in kilojoules per mole. Okay, so it's going to be 8 times 413 kilojoules per mole plus 2 times 346 kilojoules per mole plus 5 times 498 kilojoules per mole. Just trying to squish it all in here. Okay? So once you get that done, then we'll put our big bracket and our subtract sign, and then our next bracket. And then on this side we have 6 moles of carbon to carbon, or carbon to oxygen double bonds. And that's going to be 6 times 745 plus 8 times 467 kilojoules per mole. And then our big bracket. And if we work that out, I probably should have worked this out before, but now I'm going to do it with my calculator. Don't you like my fancy phone calculator? Okay, clear. And then we'll do 8 times 413 plus 2 times 346 plus 5 times 498 gives me delta H value, or sorry, a kilojoules per mole value of 6486 kilojoules. And it's really still per mole, but now it's per mole of reaction. So if this reaction happened 6 times, or 6.02 times 10 to the 23 times, then we would have this amount of energy being used to break all of the bonds. And then we're going to subtract what we have on the other side here. So 6 times 745 plus 8 times 467 gives us 8,206 kilojoules per mole reaction. And so if I work this out now, I'm going to get some number that's going to be negative 6486. Take away 8206 gives me negative 1,720 kilojoules per mole reaction, just like that. And so now I have a value. What does this value mean? It means that when we combust propane, way back here, right, when we combust propane in an excess of oxygen, or exactly enough oxygen as we need, really, to give us the carbon dioxide and the water, then we're also going to get 1,720 kilojoules of energy being produced for every 1 mole of propane that gets combusted. I hope that helps. From here, you're going to do page 690. I want you to try questions 23 to 26 in the purple book. So that's from the purple book. And then once you're finished that, you can work on your lab write-up for next week. I miss you guys, and you're probably having way more fun than I am, but hopefully I'll come back with some fun tips from the AP conference that we can use in class together. All right, I'll see you on Monday. Have a great weekend.